Chapter 8, demo question number 1. A simple random sample of size 43 is obtained from a population that's skewed left with the mean of 89 and the standard deviation of 5. Does the population need to be normally distributed for the sampling distribution of X bar with the means to be approximately normally distributed Y? What is the sampling distribution of X bar? So chapter 8 is now, instead of doing one sample and saying what's the likelihood of one person spending X amount of money on gas per week, now we're doing samples that where we get, like for our group project, for example. So we're going to do one sample, which is our class. Let's say somebody asked, what's your shoe size? So we'll get the average shoe size for just our class and analyze that. But if I wanted more accurate results, what I can do is now, let's say in our class there was 40 students. I could go to a different class and get the average shoe size of that class, and then go to a different class and then get the average shoe size for those 40 students. So every time I do a sample of 40, but I repeat this 100 times. So now I have 100 results. And what I'm going to record is just the average for each of those 40 people. So I'll have 40 results, but the 40 numbers that I have are just the averages. And that's going to give me a better distribution, better results, and I can analyze that to kind of get a more accurate, true value for the entire population of LAMC as to what the true shoe size is. We call those sampling distributions when we start making now histograms of many, many means instead of individual values, like one sample with individual values. We start now collecting samples, but all those samples happen to be averages in themselves. So we call those sampling distributions, and the way we start analyzing those, we use different formulas. So the requirements are that you should have at least 30 people in your groups that you're sampling. And this one has 43. So because that sample size, it seems like 30, once you get 30 or bigger, you get pretty good results. So that seems to be like the go-to number that statisticians have agreed on, that by the time you choose 30 or more subjects, you're pretty good. So one of the requirements is that you have to have at least 30 people in each group. If you don't, then let's say you only have 25, then it has to have come from a population that was already normal to begin with. Like, let's say I was doing it on shoe size. Since it's a human measurement, that is going to be normal to begin with, because as a species, we become pretty standard. So in that case, we wouldn't have to have 30 subjects selected each time. We can get away with less because it was normal to begin with. But this one meets the sample size of the minimum of 30. So does the population to be normally distributed originally for this sampling distribution of this X bar means sample means. So the sampling distribution, the histograms of a bunch of these means, is that going to be approximately normally distributed to guarantee that? And then therefore to use the formulas that are from chapter 8. Okay, so the answer is no, it doesn't, because our sample size was large enough. So let's say, so in this case, our population didn't need to be normal to begin with. But if our sample size was less than 30, then we would say, yes, we would have had that original population needed to be normal. But we're going to say, no, it didn't, because, and then these two, we'll see which one of those two. No, because the theorem states that only if the shape of the underlying population is normal or uniform. No, it doesn't say anything about uniform. No, the central limit states that regardless of the shape of the underlying population, the sampling distribution of a bunch of means that will be graphed eventually, the distribution of the histogram, should be approximately normal as the sample size and increases. So as you're getting larger and larger, those shapes become more normal and normal when you're graphing a bunch of means and getting that and seeing what that distribution looks like. So because our sample size is pretty large, that's the one that's saying that. Okay, so now we're going to assume we're doing these distributions. And we're going to need a a calculator to do this. Let me see if I can open a StatCrunch page just to, might require it for us to do some calculations, but sometimes I just like to type in what I'm using, or I might do it in here sometimes too. But let me share that just in case I want to write something there. All right, so if I take one group of 43 and take their average, record it, and then I take another group of 43, take their average and record it, that histogram that results when I make a histogram of a bunch of means for groups of size 43 should have a center close to the original center, which is 89. So if we do this over and over again, it's going to, when we graph all these averages or means from all these different samples, it's going to be pretty normal, and the center is going to be 89. So the sampling distribution is unknown, normal, uniform, or skewed left. Note it's for if you're graphing a bunch of means. So see how it's the mean of a bunch of means, the standard deviation, or the mean here, the center, when you graph all these means of all these different groups of size 43, and then the standard deviation when you graph all these means of size 43. So the center is going to be the same as the original. This tip for one sample or for the population, it deviated by 5. But once you start graphing a bunch of averages, it's going to deviate less than 5 because those numbers, the averages, will be closer to each other than just like individuals would be. So because it's like there are already a bunch of centers that are being collected, so those won't vary as much. So we have to adjust for this. So there's a formula where we adjust for this for means, and then there's another one for proportions. So let me see if I still have that handout up where I chose, oh, I don't have it up there. Okay, so let me show you, hold on a second, let me pause it for a second. Okay, so let me share that handout that's on, that I've also posted for you on Canvas. Okay, let me move this out of the way. So this is chapter 8. So if I scroll down to chapter 8, I said to print this out, it's easier for you. All right, so here's the mean and standard deviation for sampling distributions for quantitative data when you're like measurements. So the center, if you start graphing all these means, will be close to the population mean, but the standard deviation will be less, because there will be less variability when you're graphing a bunch of means than when you're graphing just one sample. So it's reduced by a factor of the square root of n. So it depends on how big your groups are. The larger the group, the better results you're going to get. So that variability is going to start getting smaller and smaller and smaller. So it is dependent on how big your samples are. And then for the proportions, it would be this one here, the center, if you're doing like categorical data, a bunch of proportions for different groups will be pretty close to the proportion for the population. And the standard deviation is going to be reduced by a factor of the square root of n here. So it's a slightly different formula here. So let's take a look at this problem now that we know that. Well, not that we know that, but we've looked at that. Okay, so the formula here was the standard deviation over the square root of n. So for me, it'd be the standard deviation is 5. I'm just showing you what I would put in the calculator over the square root of my sample size n. My sample size is 43. So it depends on how big your groups are. You're taking these averages from. So then I would put that on the calculator. I'm not going to put it on the StatCrunch calculator. I'll put it on my own calculator. It's just kind of, it's for illustration purposes, but it's kind of a hassle to use as well. So you'll calculate it on yours. I'll see if I can do it on the calculator. Let's see if it's, and then we want to 3 decimal places, so 0.762. Let me see if I can do it. Let's see how it would work here. It's kind of cumbersome, so it's going to be 5 divided by, and it doesn't have parentheses here. So that's why it's not practical to use this, because then I have to divide it by the square root of 5. I mean the square root of 43. Let's see if it works. If I do 43, and then I'm taking the square root of that, and then I put equals. Yeah, I guess it gives it to me if I do it that order. I just don't like working with that. So then round to 3 decimal places. Make sure you look at that 4th digit to decide if that one stays or goes. But I'm going to take that off because then it's going to mark it wrong. Question number 2. A random sample of size 10 is obtained from a population where the mean is 63 and the standard deviation or the typical deviation is 15. So let's say you're getting groups of size 10 and you're asking what the typical retirement age was. So the average retirement age is 63, give or take 15 years. So 63 plus 15 and 63 minus 15 would be a spread or a little window of what the typical retirement ages currently are. But you're only taking samples of size 10, but that's okay because you're going to do many groups of size 10 and take an average of one group of 10, take their average retirement age, and then you go to the next 10 people and take their average retirement age, and then you're going to make a graph of all those averages that you collected. So that distribution, because those shouldn't vary as much as the original, like just one group of 10 would, that standard deviation will be smaller than 15 because averages don't vary as much from each other, and you'll get a nicer result, a nicer graph that's more normal as you start repeating this experiment over and over again. So, but in this case, the sample size is 10, which is less than 30. So it's asking what must be true of for us to be able to do this analysis. What must be true regarding the distribution of the population? Okay, so because the sample size was small, then it has to come from a normal population to begin with. So since the sample size is large enough, no, it isn't, because it's not greater than 30. Yeah, the population that it came from must be normally distributed. The sampling distribution has to be assumed to be normal. No, you can't assume it. You have to guarantee it. The population must be normally distributed and the sample size must be large. No, only one or the other. As long as one of those two is satisfied, then you'll get good results. So in this case, as long as we get that the population was normal to begin with, we can continue with the analysis. Okay, so assuming now that the normal mode can be used, describe the sampling distribution. So what's the histogram, the distribution of the histogram going to look like? It's going to be pretty normal. The center should be close to the original center for the population, which is 63, but your standard deviation won't be as large as for one group of size 10. It's going to be reduced because now you're graphing a bunch of averages, and that's not going to vary as much. So that typical deviation from the center should be less than 15. By how much? By the square root of 15. So you take the original standard deviation, which was 15, here it is, that's what I'm saying, 10. And you're going to divide it by the square root of the sample size. So this one's reversing it, so be careful. It's standard deviation divided by the square root of n. So that should be smaller than 15. Okay, so now let's compute it. So anytime we're computing probabilities, which are areas, we have to do it on StatCrunch. So because we're assuming that this is roughly normal, we can go to our stat calculators and choose the normal calculators. So stat calculators normal. And my mean, we're going to use these values. The mean was 63. What's nice about StatCrunch is that you can enter that little formula in here. But see how like I have some, that this is the notation. It's going to be the minus 15. So 15 and divided by the square root. So we, for StatCrunch to understand it, is XQRT. And you have to put your number that you're taking the square root in parentheses. So minus 15 divided by, so slash SQRT, the square root of, and then parentheses. Mine happens to be 10, close parentheses. And then it'll compute it for you, so you don't have to put it on the calculator separately. If you do put it on the calculator, and there's like, 8 digits that will come up on your calculator, make sure you put all 8 digits in here. Otherwise, you might have rounding issues if you just use like the first 4 numbers or what have you. Okay, so we want the probability that if we take one average of one of these groups of size 10, that their average retirement age was something less than 67.1. So notice this isn't like if we were doing ages, it'd be the average 63. What are the odds that the average age of retirement was less than 67? And we want the probability, the P. So probability is on the right. So that's what we're leaving empty because that's what we want. We want the likelihood of that happening, the odds, that space that area takes on. So less than 67 years old, and that's pretty high probability. It's like an 80% chance of that happening. Notice the empirical rule isn't here. The 63 is in the center. So if I click on that, then it kind of adjusts for that. It makes more sense, like in terms of how many standard deviations you are from the center. So this represents the histogram shape. If we were to graph a bunch of averages from groups of size 10. So it's not like an individual one sample any longer. And that will be closer to, the true values for the population because you're gathering better samples, you're gathering more samples, and you're graphing a bunch of averages instead of just one group. What's the probability that one of these average ages will be from one group will be greater than or equal to 65.2? So we'll just change it. So in chapter 8, that's the only thing we have to worry about, that the standard deviation for graphing sampling, we call those sampling distributions. Sampling meaning that you're doing a bunch of samples. We have to adjust for that standard deviation because the variation is less for those type of graphs. And we can't just put the original, standard deviation because we're not doing it for one group in this chapter. And if you do that, you're going to get it wrong. So the key word there is sampling distribution. So you won't see an X here, you'll see an X bar. So an X bar will indicate that you're now doing a bunch of means instead of an X here. That's just like this here, it says an X, that's just one individual, but this means one average, which is a different analysis. So the symbolic notation will help you to identify if you're talking about a sampling distribution or if you're just talking about one sample. The shape of the distribution of the time required to get an oil change at some 15-minute oil change facility is skewed right. However, records indicate that the mean time is about 16.5 and the standard deviation is 4.7 minutes. So on average, it's taking 16.5 minutes to do an oil change, but they advertise that they give 15-minute oil changes. So to compute the probabilities regarding the sample mean using the normal model, what would the sample size have to be? Greater than or equal to 30, less than or equal to 30, any sample size could be used, and the normal model can't be used if the shape is skewed right. Now, it can be used if it's skewed right or skewed left, the original for one sample, as long as you have a sample size of 30, because then if you start gathering means and averages, then you'll still have nice data if you do groups of bigger than size 30, even if the original graph was skewed. For the original data they have is skewed. So because it's skewed and it's not normal to begin with, then you have to do groups of sizes larger than 30 so that when you start graphing all these averages, that graph will be symmetric, regardless if the original was not, because when you start graphing means, you're going to get some nice shapes out of that. So what is the probability that in a sample size of 45, so now this is only works for groups of size 45. So we'll do 45 oil changes and then and record just the average time for all 45. So we're going to get one number that represents that group. And then we'll take another 45 cars, take the average time for those 45 cars and just record that one number, that one average for that second group and so forth. So we're going to collect a lot of averages. And then we take all these averages and we make a graph out of that. And that graph should be bell-shaped because you'll get nice results when you're collecting averages instead of individual car times. Okay, so what's in a random sample of 45? What's the probability that it's going to take less than 15 minutes? Okay, so let's enter this data. So let's see, the mean is 16.5. So let's put our new numbers here. The original standard deviation was 4.7. So 4.7 divided by the square root of our group sizes. My group sizes are 45 groups, size of 45 at a time. So we're going to divide by the square root of 45. You divide by however many people were being cars were being sampled in your case. And then I want the probability that it's less. So that will determine the inequality here. So less than 15 minutes. So let me put 15 here. So on this here, let me do the empirical rule. So the center is 16.5 minutes. What are the odds that it's less than 15 minutes? So here's an X on the X-axis. We want the probability, which is the only one that's probability is in this box. Everything else is being measured in minutes. So the odds that it's going to take less than 15 minutes, which is what they claim that you're guaranteed, is actually very low. They're not doing a very good job of complying to their advertisement. So for decimal places. But again, remember, we're doing that in a sample of 45. So we're doing a sampling distribution here. Suppose the manager agrees to pay their employees a bonus if they can meet a certain goal. So he's going to try to encourage them to bring this time down because obviously they're not meeting it's taking it slightly a little bit longer than he would like. On one Saturday, they did one of these groups of size 45, between 10 and 12. And we're going to treat this as some random sample. There would be a 10% chance that the mean oil change time being at or below what value. This is the goal established by the manager. So now they're giving us the area. And so how many minutes would it be so that the time is below or at that value if you want 10% of the cars to be meeting this requirement? Okay. So let me put this. Below means less than, right? So we'll keep that as the less than. But now we want to see where's the 10% area. If we cover 10% of that area, then that's the probability is 10%. So how many minutes would be at the 10% mark? Compute. So that would be this time here. That's 10% of the cars would fall here below this time. And then that is 90% of the oil change times would be greater than that. Okay, so that gives me about 15.6 minutes. So he wants 10% of all oil changes to be less than 15.6 minutes. That's not even meeting the requirement because that's his goal, but we're claiming that it's less than 15 minutes. I guess it's still close to it, but a little bit better than the 16.5. So maybe he just sets a small goal. Maybe next time he'll lower it a little bit more, or maybe the owner doesn't care, right? Just as long as he can get it a little bit lower, he'll be okay with, taking a little longer. Maybe customers won't complain as much. Suppose Jack and Diane are each attempting to use a simulation to describe the sampling distribution from a population that was originally skewed left with a mean of 70 and a standard deviation of 10. So Jack obtains 1,000 random samples of size 3 from the population, and notice it was skewed originally, and finds the means and determines the standard deviation of the means. Diane does the same sample, the same simulation, but she obtains 1,000 random samples of size 40. So because the data was skewed to begin with, she's kind of like doing a better simulation because she's meeting the requirement that of the size has to be 30 or larger, the minimum size requirement, where he isn't. So let's complete these parts. Describe the shape you expect for Jack's distribution of sample means and describe the shape that you expect of Diane's. Now, because he's still doing it 1,000 times, he might still get something that's slightly symmetric. She's just going to get better results. So Jack's distribution is still going to be skewed left, but maybe less skewed than the original because now he's doing 1,000 means instead of, individuals. Diane's distribution is expected to be approximately normal. Yeah, because she's meeting the requirements. Jack's and Diane's are both going to be normal. However, Jack's will have a smaller standard deviation. And sample mean. No, Diane's going to have a smaller standard deviation because her sample size was larger. So hers is going to be, she's going to have the better results, less variability in her her normal curve. Diane's distribution is skewed left. No, she's the one that did the better one. Jack's distribution and Diane's distribution are expected to be approximately normal. However, Jack's will have a greater standard deviation of the sample mean. I believe this one is it because he's doing it 1,000 times, so he's probably going to get pretty good results. But yeah, his standard deviation will be bigger, so that could potentially be true. So that's D. And then so I would go with most likely a D here. Now be careful for yours because you might have Jack doing the sample size that's greater than 4 and Diane doing a sample size that's really small. So be careful because yours that generated could be written reverse where Jack is the one that's doing things right. But for this case, because the sample size didn't meet that requirement, you're not guaranteeing that your sampling distribution, when you graph all these averages, is going to be normally shaped. You'll probably get something better than just one sample. So Jack's is probably going to be still skewed left because the sample size is still small, but maybe a little bit less than the original. So he'll slightly get better, but only Diane's is expected to be normal because she met the requirement. What would you expect the mean of Jack's distribution to be? And the mean of Diane's? The mean is still going to be the same. It should be still close to the original. In this case, it's 70 for both. Because of the population, the center is 70. It's the deviation that will be different for both of them because of due to their sample sizes. So Jack's distribution is going to have a sample standard deviation of the original standard deviation, which for my case is 10, over the square root of his sample size, which is 3. So I'm going to have to put that in the calculator and compute that. Whereas Diane's is going to be the standard deviation of 10 but divided by the square root of 40 because her sample size is 40. It says round to 2 decimal places. So I'm going to go ahead and do that on the calculator while you can do it on your calculator as well. So typical deviation for Jack's distribution will be give or take 5.77, whereas Diane's her variation is going to be, in terms of the standard deviation for her sampling distribution, is going to be about 1.58. So she's definitely getting better results because there's less variability in her graph than in his graph. But again, you might have the opposite happening. You might have Jack getting better results than Diana, depending on how the problem was worded. Again, if you need some time to do this, just pause the recording, catch up, and then continue the recording. According to a study conducted by a statistical organization, the proportion of people who are satisfied with the way things are going is 0.84. This is a categorical slash qualitative type of question because it's a yes or no question. It's not a measurement. It's not a counting. So either you answer, yes, I'm satisfied, or no. The number of successes would be those who are satisfied. Okay, so suppose a random sample of 100 people is obtained. Suppose a random sample of 100 people is asked, are you satisfied with the way things are going? Is this qualitative or quantitative? So I was just kind of discussing that because it's a yes or no question, it's categorical, and those have a quality to it. So it's a qualitative question. There's two. Because the number of people satisfied can be counted. That's true that they can be counted, but that's not what makes it qualitative. But it makes it qualitative because the responses are classified as two categories, a yes or a no, that they are satisfied or not. That's the reason why makes something qualitative, because of the type of response. A quantitative could be because it's the number that the response is giving is a numerical value, like how many times have you been to Disneyland? 8, 10, that can be counted. I can count that I've been 8 times. I can count that I've been there 10 times. So if something can be counted, then that makes it quantitative. Or if it could be measured, like blood pressure, weight, cholesterol level, those things can be measured, height, then that's also making it a quantitative analysis instead of a categorical or qualitative analysis. Explain why the sample proportion is a random variable and what is the source of variability. The sample proportion is a random variable because p hat varies from sample to sample, and the variability is due to the fact that different people feel differently regarding their satisfaction. True. Here, the variability is due to the fact that people may not respond to the question truthfully. No. Here, the variability is due to the fact that different people feel differently regarding their satisfaction. Okay, that's the same thing as A. What did it say at the beginning? The sample proportion P is a random variable because the value of P hat represents a random person included in the sample. No, this P hat does not represent one person. It represents the proportion of people who answered yes out of the 100 or however many there were. Okay. So did we eliminate B? Yeah, and truthfully, this does not represent a person. Okay, so we eliminated the other choices. Describe the sampling distribution of P hat. So now we're not talking about one group of 100, like they originally said for part A. Now we're saying a sampling distribution of a bunch of proportions. So we're taking a bunch of 100 groups of size 100. We're go to one group of 100 and see what percent of that group said they were satisfied. And then we go ask a different group of 100, and then we see what percent of those were satisfied. And we keep repeating this. And then we make a graph of all those proportions we collected among the different groups of size 100. And if we make a graph of that, of collecting a bunch of groups of size 100, but recording the proportions of who said yes, then that's going to be pretty normal. And the center will be the same as what it was for the population. And then the standard deviation, there'll be less variability in that graph. And it depends on the sample size. So for the population, it's 84%. That's the center. It's still going to be 84%. Okay. But before we do that, I got ahead of myself. We're just going to make sure the conditions have been satisfied. Since the sample size can't be too big, so it's no more than 5%. Sometimes it's worded as it needs to be less than 5%, but that they didn't give us that option. It can't be more than 5%. If your sample sizes get too big, then there's no point of doing a statistical analysis. Like, let's say there's 10 people, there's 100 people in the entire population of somebody who has a rare disease. And then you take a sample that's 99 people. At that point, you pretty much have the population numbers. You don't have to do sampling for that. So you don't want to get too big, because at that point, there's no point of doing statistics, because you'll be close to the true measurements. So there's no point. So we only do it when we don't have access to the entire population. So we want to make sure we don't get too big. So less than 5% is what we decided we can't be larger than. But then we want to be large enough. And for proportions, this is the condition that has to be satisfied for categorical qualitative data. For the numerical measurement type, which is quantitative data, you have to have a sample size of at least 30 when you're dealing with means. But here, it's not 30, it's this requirement. So it's a little bit different. Okay, we're going to take N. I'll put it here, then I'll put it on the calculator. The sample size, which was 100, we're going to multiply by the proportion. For mine, it's 0.84% for the population proportion. So the people that, for the population that are satisfied, the way things are going is 84%. And I'm going to multiply it by 1 minus 0.84. Let me do that calculation over here. That's like the, if the success is considered 0.84, then the failure is considered the rest of them, which would be 0.16 if I subtract that. So 84% of the population is answering yes, and 16% of the population is answering no. So I'm going to put that here. It's the 1 subtract the population proportion. So the failures, in other words, if I multiply those 3 values, it has to be greater than 10. And if it is, then I've met the requirement that my sample is large enough. So 100 times 0.84 times 0.16 equals 13.44. It said round to 3 decimal places, but mine isn't that large enough. So 13.44. The distribution, since it met the 2 requirements, we're going to assume that this is not more than 100 people is not more than 5% of the entire population. So then we should expect that the sampling distribution, if we graph a bunch of these proportions gathered from groups of size 100, should be approximately normal when we make that. The center will be close to the original center, which is where the population 84% are saying that they're satisfied. The standard deviation, we'll have to apply that formula that says it's the square root P times 1 minus P. I'll put the formula here first, over the sample size N. I'll put it here. You're not putting it here, put it on paper. And then P for mine is the 84%. And then my 1 minus P was 16%. So I can multiply that by 0.16%. And then I'm going to divide it by the sample size, which my problem, they said there was 100, a sample size of groups of size 100. So I think I'm going to do this one on my own calculator, because it's the one on StatCrunch is a little bit cumbersome to use. I mean, on my MATLAB. So practice being able to do that on your calculator. And it says 3 decimal places. Round, just make sure your rounding is good as well. So the standard deviation of this sampling distribution that's going to be looking pretty normal is going to be about 0.0, like 4%. So 84%, give or take 4%. Notice that the original, well, they didn't give us an original standard deviation. So they don't have to, because we could compute it from just the proportion and the sample size. Oops, that's going to mark it wrong. I forgot to erase this. Can you erase that? As soon as I had entered it, I realized that I didn't erase that. In the sample obtained in A, what is the probability that the proportion who are satisfied with the way things are going exceeds 0.86, and the sample obtained in part A. In part A, a random sample of 100 people were asked. It's not a sampling distribution. They're not doing the proportions. This is just one group of 100. So let's take a look at that. Okay, so if you don't have StatCrunch open up StatCrunch. Let's see, it has that option. I already have a open here. So because they're asking for a probability, then you know that's these over here, these areas. We need to do it on StatCrunch. Okay, so we're going to enter the mean, which for mine was 0.84. My standard deviation for this sampling distribution is 0.037. They didn't give us a standard deviation for that population, so we don't even have a choice to use another one. And then let's see, what's the probability? So what are the odds that in that proportion, that the proportion who are satisfied with the things are going exceeds? So exceeds means is higher than, so greater than 0.86. So here's, put on the tick marks here. What percent is taken up by this? So about 29% before decimal places. And then from part C, use the distribution. Would it be unusual for a survey of 100 people to reveal that 77 or fewer were satisfied with their lives? So the probability that 77 or fewer. Now this one, they gave us the people instead of the proportion. So we have to be careful here. You know, this is, you know, the percentage of people, and they gave us the actual people. So you could either put 77 out of 100 here, or you could put that 77 people out of 100 is 0.77. Either one, you could have StatCrunch do it, or you could do it on the calculator. And fewer means less than, so we would change that to a less than. So let's see what the probability. So the probability is pretty low. It's a very small part that's being shaded. Now we have to decide, is that unusual? And you have to remember, okay, how low does it have to be? How far away from the center does it have to be for it to be unusual, for this area to be considered unusual? In this case, I'm going to say it is unusual because this probability is small. It's less than what statisticians consider to be unusual, which is 5%. Now, if this percent sign was not here, then you would do the probability, which is 0.05 as a decimal instead of as a percentage. So be careful, because some problems they'll want the 0.05 and some problems want the 5%. Exit polling is a popular technique used to determine the outcome of an election prior to results being tallied. Suppose a referendum to increase funding for education is on the ballot in a large town. An exit poll of 500 voters find that 255 voted for the referendum. How likely are the results of your sample if your population proportion of voters in the town in favor of the referendum is 48%? So the sample isn't too big because it's less than 5% of the 100,000. Okay, so that's one thing. So we're okay in that sense. How likely are the results of your sample if the population proportion of voters in the town in favor of the referendum is 48.48? I'm going to assume the conditions are met. 500 seems to be big enough. So let's go ahead and open, if you don't have it, I close mine. So stat calculators, normal. So my population in favor of the population proportion is 0.48. So I'll put it here. And what's the likelihood that more than 255, so greater than 255 is the actual count. We need to change that to a proportion. So it was 255 out of 500. So you could either do the proportion yourself, or you could just put it in here, and StatCrunch will do that. But we have to put the standard deviation in here. So remember, that was the square root of, let me put it in here just to show you the notation. So it was the square root of P, which in my case is 0.48. And then continue that one. P times 1 minus P. So 1 minus 0.48, let me do it down here. 1 subtract 0.48 would be 0.52. You could do that on the calculator. So the percent for the population that favor the referendum is 58. I'm going to multiply that by the people that don't favor it, which is 52%. I'm going to divide it by the sample size, which is 500. And then I'm going to take the square root of that. So that's what goes here in the standard deviation. It's too messy to put it in symbolic notation like for means, where you could just do standard deviation divided by the square root of n. So this one, pull up your calculator and do that. And then don't round. We want to use a lot of digits, because otherwise we're going to have a rounding issue when we do the calculations. So I don't know how many to use. Maybe 5 would be sufficient. So for mine, it's 0.02234. That would be 6. So I'm going to use 6. So that's what goes in here. 0.022343. So you want to do maybe at least 6 digits that are showing up on your calculator so that you don't have rounding error. Then compute. So do the tick mark so that my 48 shows up in the middle. So this one looks like it's like 50 point something %. But here's the probability, and we want 4 decimal places. So it's like a 9% chance of this happening. You get a result this this large, or are people saying yes? So control paste. Let me erase all of this because it's just doing nonsense here. So it's 0.0897 for mine. Okay, so now you have to decide whether you had unusual results or not unusual results. So in my case, it was larger than 5%. So that's what we're comparing it to. So I didn't have unusual results, but if your results are less than 5%, then you'll say unusual. So for mine, the result is unusual, the result is unusual, the result is not unusual. So mine is between C and D, because mine was greater than 5%. Not because it's not unusual because it was not less than 5%. This one says that it's unusual because it is less than 5%. Thus, it is not unusual for a wrong call to be made in election if exit polling alone is considered. So this is what they thought like was going to represent the population, but the chance of getting that type of results is still pretty low. So that's not just like a reliable method. It could be that people didn't feel comfortable giving their true opinion, especially if it's something that's controversial. Okay, so that concludes the demo for chapter 8.